Hello everyone, this is Mr. Huebner, and in this lab we are going to be going over the concept of Dalton's law. Dalton's law. So the sum of all of the partial pressures equal the total pressure. So this is a really good lab. I'm excited to be here. Hopefully you are too. Ultimately the question is, Alka-Seltzer, how much CO2 can it produce? One tablet, that is. We're dealing with the off-brand, because as always, I'm on a budget. So you're going to need one tablet of Alka-Seltzer. You're going to need a bin to contain water. And then you're going to need a tube, nice little rubber tube, and it has, what do you call that, glass tubing through a rubber stopper. I want to be very careful because, you know, it takes me some time to make those and I don't have a lot of time. I'm also going to be using a 250 milliliter Erlenmeyer flask. Alright. Oh, of course, I need the test tube in which I'm going to be conducting my experiment. Okay. So, I'm going to pause it because you don't need to see me filling up the water. I mean, I guess I could say some jokes, but they're not good. You know, the problem with chemistry jokes is all the good ones, you know, they're argon. See, you don't want to hear me do jokes. I blew that one. Okay, I'm going to pause it. Thought I wasn't going to wear my goggles. Well, you thought wrong. Safety first. Always wear goggles. Although this lab is fairly safe because we're just dealing with dihydrogen monoxide, also known as H2O. And then your common safe medicine, Alka-Seltzer. It just kind of gives you some bubblies for an upset stomach. Stuff you'd use at home. But, just for a good example, I'm going to wear my goggles. Alright, so we got this tub of water. It's filled with water. You can kind of see it jiggle around. I don't want to jiggle it too much because we got an electronic laptop right here. Got my Erlenmeyer flask. Alright, I'm going to put it right there. And I'm going to add H2O, just tap water, all the way to the top so that the thing is overflowing. You can kind of see that. Whoop, there it is, overflowed. My hand's kind of in the way. What else are we going to do? Oh yeah. So we need to have this capped, and I'm going to, as well as I can, and I do have a couple of little bubbles in there, but what I did was I made sure I put it upside down so that it's fully loaded with water. And there's just a teeny bit of bubbles, so that's a teeny bit of air, but there's bigger places for air in this lab, so that's very minor. I'm then going to take my hose, the end of it, and let's see, before I do that, well, yeah, okay, got a test tube holder, test tube rack right here. Alright, I'm going to fill this 1/3 of water. Oh, that's the wrong size. It doesn't fit. Alright, so, looks like I'm going to have to hold it. Actually, no, I'll just put it right in there. There we go. Problem solved. So now I'm going to put this part of the tube inside the Erlenmeyer flask without getting air pockets in it. I'm going to lean it right there. Oh gosh. Got my lanyard in a way, so it's always a good idea to have all the dangles out of sight so it's not a safety hazard there. Here's my Alka-Seltzer, off-brand. And here's the next part. I'm going to have to cut this. Okay, that's not working. Let's get us something there. Guess we'll just split it with our fingers. Oh, that's a pretty even split. But as you can see, the one on the right side, at least I can see it, slightly bigger. That's where my biggest source of air is going to come in. Because what we're doing is we're only going to do half of an Alka-Seltzer at a time. because if we do one full Alka-Seltzer, I know from experience it's going to be more gas than I can hold in this Erlenmeyer flask, and then I'm not going to be able to record it. I'm not going to be able to measure it. So we got to do half at a time and then double it at the end to get the approximate CO2 that's produced from one Alka-Seltzer tablet. That's the goal. That's the idea. Okay, so here's my test tube, and very quickly, almost simultaneously, I'm going to put the Alka-Seltzer in and then cap it with a stopper. And I don't know, yeah, you can kind of see it in the video. You can definitely see the reaction in the test tube. And you can see in the Erlenmeyer flask all that CO2 bubbling. Now you can't see it bubbling anymore, but you can see the water level decreasing ever so slightly. Again, experiments are best done in person because videos just don't seem to cut it, but it's better than nothing. We're going to wait until all the fizzing is done in the test tube. It's a nice quick little lab. Ultimately, you're going to do 2 trials. Sometimes, depending upon if we don't have time, we trade data between lab groups so that we have multiple trials. Because anytime you do science, if you just do one trial, it could be an outlier and your data meaningless. So we always like to do multiple trials to make sure that the data we got is actually true data. Alright, so there's still some bubbles. If you want to do it right, you wait for all the bubbles to stop bubbling. If you agitate it, should make it react a little bit quicker. Alright, that should be, good enough. I mean, we might get a few little bits, but the problem really is this is a very rudimentary, basic, it's not a very highly graduated flask. So, I mean, it only goes from 50 to 100 to 150. So we're going to have rough data as it is. And it looks like it's right between the 100 and 150, maybe a smidge below the halfway. Halfway would be 125. I'm going to say 123 as my estimate. Oh, no, that's 120. No, it's looking like 126. Yeah, I'm going to say 126. That is my total volume of CO2 in this experiment. I'm going to press pause, and we're going to get to the fun part where we do the calculations. So don't forget that number, 126 milliliters. All right, guys. What we're doing is, this is lab number 31. Here's all the directions. We just did the lab. So here's where we're going to put our data down. 126, that's the magic number. 126 milliliters. And I just realized we didn't take the temperature of the water. So why don't we go back there and do that while we plug in some of these numbers. Right over here is our barometer. Let's see, can we see that? There it is. And it's at 162. So we're going to write 162 for our atmospheric pressure. That's millimeters of mercury. Going to get my thermometer out. Here we go. See, it's at like 19 right now. We're going to stick that in there. Oh my gosh. It's totally submerged, but that's fine. We'll get the temperature anyways there. Okay. Yeah, once we get the water temperature, then we can figure out the partial pressure of the water vapor. Okay, total pressure of gases, that's going to be 762. It's going to be the same thing as the atmospheric pressure. And all right, it's looking like 18. 18 is the temperature. All right. And that's degrees Celsius. All right. So what we're going to do is we're going to use our water vapor chart to determine what the temperature is. And it's as easy as looking at a chart. So let's plug this in. Oh, that's it. Okay, right here's the water vapor chart. And it can be kind of hard to see. Let's zoom in on that. So looking at it, we were at 18 degrees Celsius. That's 15.5 is our partial pressure of water vapor. 15.5. And how do we get the pressure, partial pressure of the CO2? Well, we got to do total pressure equals the sum of the water vapor pressure and the CO2 pressure. So that's going to be 762 equals 15.5 plus x. So essentially we're going to have to subtract 15.5 from both sides. So I'm going to do 762 in my calculator minus 15.5, and that's 746.5. So 746.5 is my actual water vapor. That's actually my dry CO2 partial pressure. And when we do our second trial, we're going to do it right now. So 762, it's the same temperature. So 15.5, 762, and 746.5, 746.5. And let's see. From the other day when I did this, we had, what was it, 124? No. 120. No, it's 128. So we'll put that down, 128 milliliters. All right, moving on. Total volume of gases produced by one whole tablet. So let's take our data of 126. We got to multiply that by 2 because that was just half of a tablet. So 126 times 2, let's do it in the calculator just to be sure. I'm getting 252. All right, 252. Standard pressures, you guys know these. If you're in millimeters of mercury, it's 760. If you're in ATM, it's 1. If you're in kPa, it's 101.3. Those are standard pressures, it's known values. And we're going to now use Boyle's law to convert our partial pressure of CO2, the volume, not the partial pressure, the volume of CO2, and calculate what the volume is at standard pressure. So our pressure 1 is 746.5, that's the partial pressure of CO2, 746.5 mmHg. Let's put that in parentheses because we're multiplying it. And we want to multiply that by our volume, which we found was 126 milliliters. All right, and then that equals our volume 2. We want to know our new volume times our partial pressure. It's standard pressure. Our standard pressure, 760 mmHg. Always if we're in mmHg, so 760 mmHg. All right, from here I'm going to take 746.5 times 126. I'm going to divide both sides by 760. Okay, 746.5 times 126 divided by 760. And that's giving me 123.8 about. 123.8, and we're talking about milliliters because it's volume. So that's what my volume is under standard conditions, a little bit less than it was under my partial pressure conditions. Correct the volume of CO2 from its partial pressure to atmospheric pressure today. All right, so we're going to do the same thing, but instead of 760, it's going to be, I believe, 762, which was our total pressure, our pressure in the room today. Okay, so doing the same thing, 746.5 mmHg, times it by 126 milliliters, and that equals V2 times 762 milliliters. All right, so I'm going to do 746.5 times 126, divide both sides by 762, and I'm going to get 123.4. All right, so it's a little bit less than standard conditions. Very similar, because we're almost at standard pressure right now. It says your experimental volume of CO2 produced by one tablet at 760 equals experimental volume of CO2. All right, so I'm glad we're doing this together, because when I was looking at it, I was like, isn't this the same question? But yeah, it kind of is. We were talking about 1/2 a tablet, but what if you talk about one tablet? You got to multiply it by 2. So 123.4 times 2 is 246.8. 246.8. milliliters. All right. Go figure. The expected volume of CO2 per tablet is 230, and I think the piece of tablet I had looked a little bit bigger. That's the one we did, so it makes sense that we had a little bit more volume than the accepted value at 760 mmHg. We did something wrong, actually. So I multiplied to 123.4, but that was at 762. We want to do the 123.8, so let's do that one. 123.8 times 2, 247.6. Okay, so a little bit different. So it's a little bit further off, but because we're using this data, not that data. All right, the expected volume. Calculate your percent error. That's accepted minus experiment divided by accepted times 100. What is our accepted? Our accepted is 230, right there, 230 milliliter, minus experiment, which was 247.6, 47.6, and then we're going to divide it by 230, and we're going to times the whole thing by 100 to put it in terms of percent. All right, so type that in: 230 minus 247.6 divided by 230 times 100, and it's an absolute, so we don't have a negative. 7.6. Wow, whoever collected this data did a really good job. That's amazing data. Yeah, because Block A today, the best we got was 19%. And then I would say Block D did do better with 13%, but holy cow, nobody got data like this. The person's a master, whoever produced that. But 7.65%, that is, it's pretty good. Why is the pressure of the gas equal to the atmospheric pressure? All right, here's some experimental error that could have gone into it. What we're supposed to do is take the measurement by making sure the line in the flask met the water line in the tub that was in. And in that case, we could assume that the pressure inside is the pressure outside. But if they aren't, if the water level in the flask is down here and the water level in the tub is up here, the pressure inside will be different than the pressure outside. So that could have been what accounted for some of our percentage error, because we didn't do that. And one of the reasons we didn't do that is because it's tricky, because you risk, if you move it, letting the air out, and then that would be even more error. So, yeah, so we made the assumption that they're equal, although they kind of weren't because of what I had just said. All right. If water levels in flask and tub were the same, you could assume the total pressures are equal. Okay. All right, 8 and 9, we're going to quickly run through these guys. We got 2,100 milliliters of CO2 collected over water. And the water levels are equalized. Determine the volume of CO2 at standard pressure. Atmospheric pressure is 746 and water temp is 24. All right. Looks like we've got temperature, pressure, and volume. So I'm going to have to use the combined gas law in this case. That's 2,100 milliliters times our pressure, which was 746 mmHg, divided by our temperature of 24, but it's got to be in Kelvin, so we take 24 and we add 273. Type it in your calculator, you get 297 Kelvin. And this equals standard pressure. We want to figure out what is the volume. So we're going to do V2 times our standard pressure. Since we're in mmHg, I know 760 mmHg is standard pressure. We divide that by standard temperature, which is always 273 Kelvin. All right, so solving this out, I'm going to do 2,100 times 746 divided by 297 times both sides by 273, divide both sides by 760. I'm getting 1894.7. 1894.7 milliliters. So this is my volume under standard conditions, where it was 2,100 under the non-standard conditions. So the next question is, how many Alka-Seltzer tablets would you produce? Since under standard conditions, 230 milliliters is equivalent to the amount of CO2 produced by one tablet. Well, how about 1894 milliliters? So we're going to take 1894 divided by our 230. Where is it? Divided by our 230. So take that divided by 230. I'm getting 8.2. So I need at least 8.2 Alka-Seltzer tablets in order to produce 1894 milliliters of CO2 gas. Now, 230 is Alka-Seltzer. Were we using Alka-Seltzer? No, we were using the Walgreens off-brand. Why? Because I'm on a budget. So maybe 230 is not the accepted value for the Walgreens off-brand Alka-Seltzer. So there's a lot of factors in here that could skew our data and things we need to be aware of when we're doing these experiments. So that is that. That's as far as I'm going to get on Dalton's lab. And I hope you enjoyed yourself. Until next time, have a very good day.